Just remember, in this, we have pure substances. Everything, when you're looking at a pure substance, it's matter that's made up of only one kind of substance. So you can think like the particle, they're the same throughout. They can be elements, which means that they're all the exact building blocks, all the same atoms. Compounds, though, are all the same building blocks, but there's more than one atom in each building block. So still uniform throughout. Remember, with pure substances, you can't physically separate them. So you couldn't filter it, you couldn't boil it, you couldn't try to divide it and actually separate it into different parts. No matter how small you separated it, you can't physically separate them. You would have to separate hydrogen and oxygen in a water molecule by chemically breaking that down. The thing that sometimes throws people is that pure substances tend to look homogeneous. So when they look, they're like, well, from what it looks like, is it a homogeneous mixture or is it a pure substance? Just because it looks the same throughout. Really what you have to think about is, what is it telling you? What is it composed of? So if you see one of the elements that's on the periodic table, then you know it's a pure substance and an element. And if you look and you're given a formula where you have more than one symbol in the formula, then you know it's a compound, okay? But if you see something like salt in water, then you're talking about two things that now have been physically mixed together, stirred together. That's when you're talking about a mixture. So that may look homogeneous, but it's made of two or more pure substances that have been physically combined. So we'll look a little more at there's that dynamic study module. We'll do a couple of those once we get finished with this. So looking on the periodic table, and I gave you the laminated copy, so I'll always give you this. I always put this out, but I also gave you the paper copy. So if you're looking at the periodic table, the rows which are going across are called periods. As you go across on the periodic table, the elements get bigger. So you can tell that if you look at the periodic table, that number in the big chart, it's the number on the bottom, the red. And if you follow across, you see that increases. The numbers on the top, they increase as you go from left to right. The columns are called groups. So when we're going across, it's the periods. Groups are the columns running across. There's really a couple of groups. One, this first column, they call them the alkali metals. So column 1, all the way on the far left, starts off with hydrogen, lithium, sodium, potassium, all the way down. They call those the alkali metals. And the group that's all the way over next to the last on the right, which is fluorine, chlorine, bromine, and iodine. And if you're looking at yours, do you see where it's over? It's like column 7A. Those are called the halogens. The last column, which is column 8A, those are the noble gases. So they are helium, neon, argon, krypton. And in fact, some of these were the last ones to be discovered because they don't react typically with other elements. So they typically just exist as elements in the environment. They're not reactive, they're very stable. That's how they got their name. Sometimes they're called the inert gases, like non-reactive, or the noble gases. But those ones are sort of common column names that you have. The other great big thing that you can tell from the periodic table, and you can actually tell it better on this than you can on that, is you notice this like bold line that comes down just to the left side of boron, number 5 in column 3A. And you see it kind of makes this little stair step or zigzag. Well, it's a very fancy name. It's called the zigzag line. And what it does is it actually divides the elements into metals and nonmetals. So if you find boron, you'll see that bold line that runs all the way down. There's a silicon, astatine. It continues on, but you can find it on the periodic table. Everything that is to the left is a metal. So when you're looking at the periodic table, most of what you see is a metal. Everything that's to the right is a nonmetal. And this will come into play when we are talking about bonding, reactivity of elements, why elements combine to form molecules. To a large extent, this characteristic is a good and easy way to predict when elements will actually combine. So remember, everything to the left is metals, everything to the right is nonmetals. Lots more metals than you have nonmetals in the known elements. Right along the line, like the boron, the silicon, those ones, they call them metalloids because they're kind of like a metal, kind of like a nonmetal. So in this, here's my list. I thought that I had it straight. Metal properties. So when you look at a metal, it's like 3 slides forward, then we'll go back. When you look at a metal, what are typical characteristics of a metal? Like, what do they look like? Are they solids, liquids, or gases? Solid. Yeah, so metals are typically solid at room temperature. They can be bent. They can, or have, they're able to be shaped. Mm-hmm. Some metals, you can actually pull them into a wire. That aids in their ability to conduct electricity. So solid at room temperature, you can pound them or shape them. They can be pulled into wires and they're called conductors. You might learn this the hard way, like if you were a kid and you stuck something in the socket, stick something metal in a socket, that's the worst plan ever. We had a little night light and I was swinging like a necklace, a metal necklace, and I like wrapped around it and like hit the prongs and I was like, I think all my hair like stood on end, is what it felt like, okay? Wouldn't happen if we'd used a non-metal, okay? But metals, good conductors, can be a problem. Non-metals, on the other hand, they're almost like on the opposite spectrum. So non-metals, when you're looking at them, you have nitrogen, oxygen, fluorine. Are those solids, liquids, or gases? They're gases. Mm-hmm. So those are the ones that are shown in red. Nitrogen, oxygen, fluorine, and chlorine, and then all the noble gases. They all exist, so most of them exist as gases. The black, ones that are colored black, those are solid. Okay, so notice the 2 blue. Okay, mercury is a liquid metal at room temperature, and bromine is a liquid non-metal at room temperature. So even though they're on opposite sides of the zigzag line, one of them's a metal, one's a non-metal, but you would say that most of your non-metals are actually gases at room temperature. Those that are solid, phosphorus, sulfur, selenium, they're very brittle. So you can, they're just kind of powdery, so you can't pound them into anything that has a shape or a structure, unlike if it's a solid nonmetal, it's very brittle, doesn't form a wire. And in fact, they're not conductors. So these are actually good insulators. So they will use these to insulate and block electricity from being able to be conducted. So using these nonmetals and the ones right along the zigzag line, this actually allowed the development of this whole computer age. Because you could take what used to take wires, like computers that they used to have back in the 60s and 70s, took up huge rooms, and they had these big like wheels, and they had like actual wires like you wire a house. That's how they would do its processing. When you could take those wires and make them microscopically thin and lay them in something that was not conductive, you could suddenly put wires really close together, because you could put a non-conductor in between and it would act to insulate it. And so the sort of understanding of non-conductors helped an awful lot in making these large processors get smaller and smaller and smaller, so that now these little computer chips are just like, they're just not much bigger than like a dog kibble. They're teeny tiny in comparison to the size that they used to be. So they use both of them with them. So those ones that border the line, they call them metalloids. And metalloids have a little bit of conductive property, a little non-conductive properties. They're sort of a little like a metal, a little like a non-metal. So what you'll notice in the periodic table is you either see one letter for their symbol or you see two. What do you notice if there is a second letter? It's always what? It's always lowercase. Okay, so the first letter, or if there's only one letter, it's uppercase, it's capitalized. The second letter, if there is one, then it's always lowercase. And that's going to allow you to look at a formula and actually determine how many elements there would be in a compound. So if you had MgSO4, magnesium sulfate. So seeing that, you don't just count the number of letters, but you actually look at the capital letters. So Mg, that's one element. S, that's one element, and then O. So that has three elements in it, and you can remember this because it's got those capital letters. This is good and beneficial because that makes this and this different. Capital C, little o, that's cobalt. Capital C, capital O, that's carbon monoxide. So when you're writing your formulas, always make sure if you have a second symbol, always make it lowercase. And that way it's never mistaken for something else, for being two elements instead of one. So the ones that you need to know. So you need to learn the first 20, okay? So 1 through 20, those really include the big ones. That includes carbon, hydrogen, oxygen, and nitrogen. And it really includes a lot of the minor and trace elements that you find in the human body. So you want to, and you could do this like as a flashcard thing, or you just put the symbol on one side, name on the other side. So it's just purely the name and the symbol. So if I give you the symbol, you should be able to give me the name and vice versa. But then there's some other ones that we're going to talk about. So I've added those ones in. So in those, we have going across chromium, Cr. Chromium on the periodic table is number 24 going across. Continuing on, Fe, that's iron. And Fe and Na and K, they don't typically have their normal symbol based on the name. And that's because like they were running out of S's. They like had, so you had sulfur and you have selenium, you have scandium. So there's a lot of S words in there. So when they got sodium, instead of using an S or an SO, they took the Latin term. So sodium is one that's kind of odd. It's Na. And it actually comes from the Latin term natrium, which is where the term salt derived. So that one, an S, is sometimes mixed or flipped. People make mistakes. S is sulfur. The other one is K. So K comes from the Latin kalium, which is potassium. So those ones are both in that first column, those alkali metals.
So these being having name, some of them being Latin name.
Yeah, they're all, that's the ones that are the oddballs, like iron, Fe, that comes from the Latin ferrous or ferric. And so that's where that symbol derived from instead of an I, because they had iodine already. Okay, so instead of doing an IR, they actually went to the Latin term. They didn't do it with all of them, just the weird ones. So Fe, iron, keep that one straight. A lot of people will mistake if I give you P. P is not potassium, P is so C15. That is phosphorus. Okay, so in your book, in the front cover, you have the names and symbols. Okay, so you can use those. You don't have to learn all 118 because that's a little bit old. There is 118 elements now. Just stick first with 1 through 20. So go through and make a list of each of the elements' names and their symbols for 1 through 20. Then add these ones in. So chromium, Cr, iron, Fe, cobalt is Co, capital C, little o. Copper is Cu. Both of them start with Co, but copper end up, and that comes from cupric or cuprous. Zinc is Zn. Bromine, Br. Two precious metals, so silver is Ag, gold is Au. And then the last one's mercury, because we're going to talk about like pressure, so we're going to talk about measurements in millimeters, mmHg, millimeters of mercury, and that's its symbol. So it's about 30. Oh, iodine, there is 30. I was like, there's only 29. There's 30, so iodine is I, so add that one too. So the reason that I picked these, one has to do with bonding, so we'll see bonding. The other one is also, some of these are found in the body as some of the trace elements, so we'll talk about them too. Like I said, with pressure, we're going to talk about blood pressure, atmospheric pressure, so millimeters of mercury is used. So that's where being familiar with these 30 would really serve you well. Okay, any other ones? Like I know when we talk about radioactivity, we're going to talk about like uranium, which is a U, but I would always tell you what that one is. So these 30, you should know names and symbols, but if I asked you about any others, I would give you the name and the symbol in the question. So I wouldn't expect you to just automatically know what that one would be. Okay, so things to remember: going across, they call that a period. Going down, they call that a group. The way these are arranged, this is not random. There's information that you can tell from the periodic table being arranged this way. One, all of the blue, those are all the metals. All of the yellow, those are all the non-metals. That zigzag line is a separation. And you see those green ones. So those green ones are the ones that I said are kind of like metals, kind of like non-metals. They're the ones that they call metalloids. Important elements is found in the body. I use like mnemonics in trying to remember things. That sometimes helps me. So the mnemonic I remember for the main group elements is CHM. So CHM's not really a word, but so it's carbon, hydrogen, oxygen, and nitrogen. They're considered the main elements because 96% of the elements found in your body are carbon, hydrogen, oxygen, or nitrogen. These are really the elements that are used to build carbohydrates, proteins, lipids, and nucleic acids, the big biomolecules that are found. But then you have what are considered like the minor elements. The minor elements are those that you don't have to have every day. You need to have in smaller quantities. These include sodium, potassium, calcium, magnesium, chlorine. So these macronutrients, I always consider them minor. Altogether, they make about 3.9% of the elements in the body. So if you added them all together, there's phosphorus, sulfur falls into this category. We have 7. Iodine and iron are pretty close in there. And then the micronutrients. So micronutrients you need very, very little of. Okay? So they are altogether only 0.1%. So they're a very small amount. They sometimes call these trace elements. There's about 15 of them. So there's a lot of them, but they're found in very small amounts. So examples like zinc, selenium, copper, cobalt, molybdenum, some of the really oddball ones. So they're not ones that all your cells use, but some of your cells require them. They don't require them in a very high amount. They did a list, like kind of a picture, so that you can see some of them. And you can see in this one, they did put phosphorus and sulfur in. The yellow, that's your CHM, those are the major. Then you can see the 7 minor. And then it shows you some of the trace elements in purple. There's actually a couple more than that. But a good example, so like with iron. So iron is important because you put it into what? What cells contain iron? Red blood cells, okay? So you don't need iron in order for your skin cells to function, okay? You don't need iron in order for bone cells to function. It gets put into red blood cells and it helps with oxygenation. So that's where it falls into that trace element. Certain cells within the body require these, but they're not required by all. Fluorine. What's fluorine important for? It's another trace. Yeah, it helps to harden teeth. It helps to resist acid breakdown of the enamel of your teeth. So that's pretty specific. So you don't have to have large amounts of it. Those are the ones to remember that those are considered those trace elements. So when measuring elements, when measuring compounds or making up mixtures, measurement comes into play, and in chemistry we use metric. Okay, so in the United States, a lot of our measurements are all done in English units. So the United States does this, and some parts of Australia. That's pretty much it. Like all of the other countries, everybody uses this metric system. And so it's actually a whole lot easier in the metric because you don't have to remember all those numbers. So the numbers I'm talking about is like, so with length, so the small little unit of length when you're talking in English units is an inch, okay? So it's about this big. And it was actually like, they used it as like the length of someone's finger. So it was a way of like this generic measurement that was adopted. So you have to remember inch. And then in order to scale up, to get a foot, you have to remember what? And how many inches in a foot? Yeah, you got to remember 12. Why 12? Well, that was like the length of the average man's foot. And so they took that. So that was like used by cobblers. So it's a foot. So that's where the name came from, the terminology, and the actual measurement itself. So we went from that, and then we go to feet, and then yards. And a yard is the average length of a man's pace. So as a man would be walking steps, that would be a yard. So that was like picked up, the pacing off of land. They did it in yards. But then you've got to remember how many feet in a yard. You have to remember how many inches in a yard. You have to remember these numbers in order to convert from one to the other. So it really adds a lot of challenge to it. I think volume is one of the funniest ones because you have the smallest in volume, measuring out liquids. You can have an ounce. And then in 8 ounces, that makes a cup, right? But then you have to remember that 2 cups makes a pint. And then you have to remember that 2 pints makes a quart. But then it's not 2. Then you got to remember that you have to have 4 quarts to make a geez, right? So all of those, like you have to remember all those numbers in order to, and they seem almost like random, but like literally a cup is like the cup that they used to use to scoop out flour or scoop out grain. That then became the cup. Like that's how that amounts. And so then pints was a big mug, like what you would put beer in. And so that you would have a pint of beer because no one drank water. You would get sick and die. So everybody had to drink beer because they didn't have any sanitation. So you would like ferment your water and that way you would be okay. So in order to go to all of these, you have to remember all these crazy numbers. Metric takes that out. With metric, for me, you really only have to learn 5 things. You just have to remember what the prefixes stand for. And then you can convert to anything, whether it's length or volume or in mass. So this, the standard for mass, for weight, in metric is called the gram. So the gram is really small. Like a gram of salt is like 1/8 of a teaspoon. So it's just like small grains. And we'll be using the balances in lab, so you will get more experience with measuring out grams. And you'll see it's a very small amount. When we use it in terms of health, you're usually talking about people's body weight, and instead of talking about grams, you talk about their kilograms, okay? Because that's going to scale it up. But it's pretty easy to remember that difference. Liter is volume, and I'll say of all the 3, this is the one most embraced within the United States because of what? The 2 liter. Because of the 2-liter soda. So everybody knows. Everybody is like, oh yeah, I know what that is. Okay? And there's like, it's much more common, like, so this is a 1-liter bottle. And it's like skinny, so it fits in my little cup holder. And so it'll like last longer than just the regular 16.9, which is a 1/2 liter. So the standard volume for liter length, it's meter. And the funny thing, meter is just a little bit longer than a yard. It's not much difference. That one's really pretty close. So in looking at the 3 different types of measurements, mass, volume, and length, we can indicate sizes larger or smaller just by using a prefix. And this prefix works with all 3. So you don't have to remember cups and pints. You don't have to remember inches and yards. You just have to remember these prefixes, and then they work with all of them. So the ones that I use the most are those 5. Kilo, deci, centi, milli, and micro. So this prefix is put in front of the base unit. It's put in front of grams, in front of liters, in front of meters, and it indicates if that number is a larger or smaller measurement. So when you see kilo, the term kilo means that it's 1,000 times larger than the base unit. So if we have 1 kilogram, it would be 1,000 grams because kilo is 1,000 times larger. If you had 1 kiloliter, that would be 1,000 liters. So whenever you see kilo, you know that that base unit is going to be 1,000 times larger than its number. That's the only one that's larger. All the other ones are smaller. So deci, and I always think of decimal when I think of deci. So deci is just 1 decimal difference. It is 10 times smaller. So that means that I have to have 10 decis to make a base unit because it's a smaller value. So it takes 10 decimeters to make 1 meter. It takes 10 decigrams to make 1 gram. So you see the difference between kilo and deci. So kilo is larger. It takes 1,000 base units to make a kilo of anything. But the other ones are all smaller, and so they're all going to have the numbers based on 10 to make a base unit. Centi, I think of a century, or I think the number pennies in a dollar. So centi means 100. This is 10 times smaller. Sorry, 100 times smaller. I wrote 100 and said 10. So in this, anytime you have a centi, that means that it takes 100 of them to make a base unit. So if I have 1 gram, how many centigrams? It's going to take 100. If I have 1 meter, how many centimeters? 100. Okay, so in front of centi, you always put 100. In front of deci, you'll always put a 10 when doing the unit conversions. So milli, where are you looking?
Introduction to computers.
That, do you have the?
Yeah.
Is that this one or up there?
It's this one.
Oh, so 42, that's building D.
Okay.
Okay, so that's like, it's kind of like the very back, building.
Okay.
Okay, sorry. Wrong building. Milli, think of a millennium. Okay, so milli means 1,000. Okay, so milli is 1,000. Anytime you see milli, you know that you're going to put 1,000 in front of it. So 1,000 milliliters is what you have to make a liter. 1,000 milligrams is what you have to make a gram. Deci, centi, milli, all smaller unit size. Micro is like microscopic. So micro is the smallest. Micro is 1,000,000 times smaller. So you have to have a 1 in 6 zeros. So because they already had milli and they gave milli the little m, so micro comes along, another m, and they're like, oh, so what are we going to use? We're going to use this Greek symbol that's called mu. Okay, and it looks like a U with a foot on the front. Sometimes mine don't always look great, but it sort of has like this foot extension sticking down first. That's what micro is. So if you want a gram, how many micrograms do you have to measure out? So in order to make 1 gram, I'd have to measure out 1,000,000 micrograms. So if you see micro, you're going to put 1,000,000 in front of it. If you see milli, you're going to put 1,000 in front of it. Centi will have 100 in front of it. Deci will have 10. Those are the only ones you have to learn. Okay, those 5. If you commit these 5 to memory, we can convert to anything. We can look at length, we can look at volume, we can look at mass. We do this by making what's called a unit conversion. And so it's really like saying this is equal to this. So remember we said it took 10 decis to make a base unit of anything. So 10 decigrams equals 1 gram. That's what we said on the previous page. 10 decigrams is 1 gram. So since they're the same, we can put them on top of each other, or we could put them on top of each other opposite. It's saying the same thing. Best example is, how many units in a dozen? 12. So 1 dozen is 12. So you could put 12 per dozen or 1 dozen per 12. It's saying the same thing. It's the same unit. It's just saying it in different values, like 12 inches in 1 foot, same thing. So what we're saying here, though, is we're using metric, and we just have to use those 5 values, and we can do it for all of the different ways of measuring. So in this, they call this dimensional analysis. Now, you may have done unit conversions like by using a number line and moving your decimal place by a number line. The only challenge with that is if you miss one. So if you miss one, you may actually be off in your dosage calculation by a factor of 10, and that could have very serious consequences. If you set it up this way, then the only way you're going to get this wrong is if you put it in your calculator wrong, okay? Or you just don't move the decimal places the right number based on the problem. But in this, we're always going to set it up. We're going to be given, you'll have a given unit equals a desired unit. And you can go from one to the other just by setting up the ratio. You always put the given unit on the bottom initially, because what will happen to those unit values? They'll cancel out. So given unit and given unit will cancel out, and it'll leave you with the unit that you want. So remembering this, let's do this one. And I wrote those ones up at the very top. So if we have 24 milliliters, we want to know how many liters. So in this one, you always start with the unit you're given. So we're given 24 milliliters, right? And then you do times in a line. So now we're going to put a conversion unit. What unit do I want to put on the bottom? The one I want to cancel. So I'm going to put milliliters goes on the bottom. Okay, so the unit you start with always goes on the bottom in the first step. What's the desired unit? What unit do I want? Liters. So that one goes on top. What did we say? Every time you see milli, what goes in front of it? 1,000. So 1 liter over 1,000 milliliters, same measurement, different units. So that's going to allow milliliters and milliliters cancel. And when you do this math, you take 24 and you divide it by 1,000. So you take everything on the top gets multiplied, everything on the bottom gets divided by. Okay, so you want to do each one. So in this, you end up with 24 divided by 1,000. Our answer's in liters. Does anybody not have a calculator? So I brought all my calculators with me. If you have your phone, you can use that if you want to borrow a calculator. Anybody else want to borrow a calculator? Got one? Okay, so 24 divided by 1,000. Decimal place goes to the left by the number of zeros in that 1,000, so it would go 3 places to the left. You can use your calculator. You'll always be able to use a calculator on a test. So you should get 0.024. Yes? Okay. Try the next one. Set it up same way. So what did you write down first? So what you're given, you put first, and then times and put a line. So what unit goes on the bottom? Grams. Whatever you start with, that unit always goes on the bottom in the first step. So what's the unit we want to go to? Kilograms. Okay, so that's going to go on the top. That's going to allow those to cancel. So grams and grams will cancel. Now comes the challenge. If this will actually come off of phrase. So now comes the challenge. Which one's bigger? Kilo. So that means that kilo gets the 1 and the base unit gets the 1,000. Okay, so if you look the top, when you see kilo, kilo gets the 1, base unit gets the 1,000. With all the other ones, they always, the prefix value gets the number. Kilo is 1,000 times larger than a base unit, so it gets the 1. Grams gets the 1,000. Units still cancel. Take 97.1, divide it by 1,000. Don't drop numbers off. Keep numbers when you do unit conversions. Okay, we'll talk about rounding, but when doing a unit conversion, that doesn't come into rounding properties. So if, that first one, liters is the base unit. Liters, grams, meters. If one of those is one of your units, this is all you have to do. It's just one step. You can go from milliliters to liters, you could go from liters to milliliters, you could go from grams to kilograms, you can go from kilograms to grams. It's just a single step, just like this. Okay? If you have a base unit as one of your unit values, it's a single step. But look at these two on the bottom. So these two, you have decigrams, that's a prefixed unit, and you have milligrams, that's a prefixed unit. So to do this, you don't have to work on a number line. You just do it in 2 steps, okay? So in this needs to be 2 steps. When you have 2 prefixed units, you're going to do it in 2 steps, and you don't have to remember anything except what's at the top. If you do it in 2 steps, you're going to go from decigrams to grams. And then from grams, you can go to milligrams. So we're still going to set it up the same way. We're just going to have to set up 2 unit conversions. So in this one, 4 decigrams, 4 dg times in the line. What unit goes on the bottom in the beginning? Yep, so whatever you're given, that always goes in the bottom in the first. In that first arrow, I want to go to what? Grams. Okay, so you're always going to go to the base unit first because we know how many decigrams in a gram. Deci means 10, so deci gets a 10, grams gets the 1. Anytime you have deci is going to get the 10, centi would get 100, milli would get 1,000, micro would get 1,000,000. It's only that kilo that throws everything off. But we're not done because we're now at grams. So you see that these units will cancel. So now we got to do that second arrow. So in the second arrow, times in the line, what's going to go on the bottom now? Grams goes on the bottom because that's the unit I have. So now that's the unit I want to get rid of. So in the second step, the base unit goes on the bottom, and the unit you want to go to, in this case it's milligrams, goes on top. When you see milli, what you put in front of it? 1,000. So put 1,000 in front of milli, grams gets the 1. So you only have to remember those 5, and you can do conversions of any of those, any combinations of those 5 in any different form of measurement. Grams and grams will cancel. So now in doing the math, you multiply everything across the top. So it's 4 times 1,000, because anything times 1 doesn't change. So if you have something times 1, you can ignore that. It's not going to change your number. But 4 times 1,000, and then divide it by each thing in the bottom. So you want to divide it by each factor. So you divide it by 10. You see that all of our units canceled except the unit that you wanted. And so this would be 400. So follow the same premise and see if you can fill this one. Okay, so what are you going to do in the first step? What goes on the bottom in the first step? Millimeters. And what goes on the top in the first step? Meters, right? We're going to do it in 2 steps. So the first step is to always go to the base unit. Okay, so we're going to go from millimeters to meters and then to centimeters. And then on to centimeters. So when you look at this unit conversion, meters and millimeters, milli gets gets 1,000. So milli gets the 1,000. Oh, sorry. That's going to allow these to cancel. But I'm not where I want to be. I want to get to centimeters. So I want to do one more step. What unit goes on the bottom in the second step? Meters. So the unit that you have left now goes on the bottom. And then the unit you want to get to now goes on the top. When you see centi, what goes in front of it? 100. Meters is the 1. Meters and meters will cancel. And doing the math, 8.068 times 100 divided by 1,000. Everything across the top, divide by each thing in the bottom. At 0.8068. Yes? So it's a matter of doing just a single step or doing a double step. Next week in lab, we will do a lot of these. If you haven't done a lot of unit conversions, in that handout that I gave you, the one that's this, that second page, 2 pages of unit conversions. The answer keys are posted in Moodle. So if you want to go through and continue to practice them, we'll do another one at the very beginning of class next time, do another couple ones. So that's like the next page. I'm going to skip those, you work on them. But it's really just a matter, again, of this practice. Set it up the same way each time. So this comes into play like when you're doing dosages. So sometimes medication may actually be in one concentration and what the doctor's orders are different. And so being able to put them together, because it's the same as trying to say, well, we have 789 inches and you have to give 3 feet. You're like, what? Wait a minute, I have to do the math to figure out exactly which those are. You can't compare the apples and the oranges. You can't compare micrograms and milligrams. You have to put them on the same scale. So in this one, the doctor orders 0.25 milligrams of digoxin, and you have a solution, which is the medication dissolved in a liquid of 500 micrograms per mil. So you know how much you have to give, but see, that's in milligrams. The solution is in micrograms. So you'll have to convert one to the other. So 0.25 milligrams is equal to how many micrograms? So set this one up. Where are we going to go to first? And then from there to micrograms. So you start off, you put 0.25 milligrams times in the line. What unit do you put on the bottom? Milligrams on the bottom. So what you start with always goes on the bottom in the first step. And then what goes on top? Grams. Milli means what? 1,000. So you put 1,000 in front of milligrams, 1 for the gram. That's step 1, times in one more line because we've got 2 prefixed units. So now, what unit goes on the bottom in the second? Grams. What unit goes on top? Micrograms, because that's where we're going. When you see micro, you have to put a million in front of it. So you put a 1 million on the top for that second. Grams gets a 1. So you put a million up top. Make sure you count your zeros. I'm bad about that. Then, see milligrams and milligrams, grams and grams. They'll cancel, so you know you set it up right. Now it's just a matter of doing the math. So 0.25 times million divided by 1,000. Multiply everything across the top, divide by each thing other than 1 on the bottom. That's right. So this is 250 micrograms. So if I want to give him a solution of 500 microgram, if that's 500 micrograms per mil, and I want to give him 250 micrograms, how do I set that up? So when you look at those units, what units can I get to cancel in there? I can get micrograms to cancel. So if I have 250 micrograms times in a line, that 500 micrograms per mil is like a unit conversion. So what am I going to put on the bottom? The 500 micrograms goes on the bottom. The 1 milliliter goes on the top. So my solution concentration, I set it up, and the units then will cancel. And it'll tell you how much you end up giving. 250 divided by 500 would be? $0.5. So that's where being able to go back and check, looking at units, sitting down and actually converting them. If you're using the same ones over and over again, it becomes kind of rote. So you know you have to give this amount because this is the concentration. But when you're starting off, it's really good to double check this, to sit down and actually set it up so that you can see how these numbers can interchange. And the nice thing is you just got to remember those 5 things. You just have to remember, what is kilo, deci, centi, milli, micro? What do those terms mean? How do I use them in a unit conversion? You don't have to remember 12 or 360 or any of those other numbers like with English units. Like I said, next week we'll practice them. This slide, we'll do a couple of those. These come off of those practice worksheets that I gave you next time. So the other big math thing that they talk about is significant figures. And this also always throws people, but it's really pretty simple. Significant figures are just how important are measurements, okay? So if you say, it's about 10 inches, or if you say that it's 10.50 inches, how exact are your numbers, and how do you know when to round? Like, so with these answers, do you just like drop a couple of the numbers off? How do you know when to round? These actually tell you the correct way to round measured numbers. So a significant figure in a number, any number between 1 and 9, okay? Any number between 1 and 9 is considered a significant figure, which means that it's part of a measurement. So really, that only leads zeros. Zeros are the only numbers or the only place units in a number that tend to lead to problems. So in this, they say zeros are the troublemakers. Zeros sometimes just hold a decimal place, that they're really not part of a measurement. They're just indicating like a size change in the unit. So they have leading zeros. A leading zero is a zero with in front that has a decimal place. So my example with that is like 0.0025. Those zeros are not significant. Those zeros are just indicating that this is 25, that's tenths, hundredths, 25 thousandths in terms of its size. But the 2 and the 5 were the measured numbers. So those would be, this would be 2 significant figures. They call them sig figs. So there's only 2 significant figures in that number. Any number between 1 and 9 is a significant figure. Lagging zeros. Lagging zeros are also not considered significant figures typically because they estimate really big numbers. And so you're like, I have $1 million. Do you have exactly $1 million or do you have $999,999? Okay, so when you say I have $1 million, wouldn't that be nice? If I have $1 million, that's sort of a general number. So really, only the 1 would be considered significant. The other zeros are just holding the size of the number. So in mine, I said 12,000. So in 12,000, those lagging zeros, which means zeros at the end of a number, lagging zeros are not significant unless there's a decimal. Because when you put a decimal in, now you start to actually define what is a measurement. So a lagging zero with a decimal are considered measured places and they're significant. So look at this number right here, 0.001250. How many significant figures in that number? There's 4. The 1, the 2, the 5, and the 0. These are not significant. Leading zeros are never significant based on the first rule. Leading zeros out front, never significant. But this one, because I have a decimal place, any zeros at the end are kept. They're considered significant. So this is 4 significant figures. Zeros in between non-zero numbers is the only other place you'll find a 0 in a number, like 12,001. So if I have 12,001 pennies, that means that I counted to 12,001. But if I say I have 12,000 pennies, I might have 11,999, or I might have 12,002. That's more of an estimate in terms of size. But if I say I have 12,001, that means that those zeros are actually holding a measured number. So how many significant figures in this? 5. Okay, so when we do unit conversions, like, we say you put 1,000 in front of milli, that you put 1,000,000 in front of micro, those are part of unit conversions and they're called exact numbers and you really don't count them when you're doing any kind of calculations. So let's look at a couple. So you tell me in this, how many significant figures? And use that page where I gave you the rules, especially about the zeros, because the zeros are the ones that everybody has problems with. How many significant figures in that number? 6. Very good. The 0 in front is not. Zeros out front are never significant. Okay? But the 0 in between, that is. That means it was measured at that 0 place. So this has 6. 12,500 liters? 3. Lagging zeros are not significant unless there's a decimal place. 456.00025 centimeters. Yeah, all of them. Okay, zeros in between, those are considered measured values. 0.0025896 decigrams. 5. The zeros out front are not. 0.0045100 kiloliters, sorry. 5. Because of the decimal. So when you see the decimal, any zeros at the end, they become measured values. So see how this and this, how those are different. Okay? When you have a decimal place, then those zeros at the end become measured values. That one, this is like the only way you could measure something and say exact. Like if you wanted to say, I have exactly 1 million millimeters. How many significant figures? There's a decimal place. So in that one, if you have a decimal place, that is a way of actually indicating that's an exact, like that I measured that exact. So if it just said 1 million, it would be 1. But if I said this is exactly 1 million, you would put that the million, and that decimal place then makes the lagging zeros, the ending zeros, significant. Zeros at the end of a number are significant if there's a decimal place. 7? Yeah. 6 zeros in the 1. Okay. Zeros at the end of a number, if there's a decimal, doesn't matter where the decimal is, but if there's zeros at the end of a number are significant if there's a decimal place. Okay, but like 12,500, no decimal place, those, you don't count those. That's considered just like holding the size. 9,500, 0.120 decigrams, all of them, right? So the zeros in between are, and the ones at the end because you got a decimal. So they're not too bad. It's really the practice and the recognition, okay? Leading zeros are never significant. Lagging zeros are not significant unless there's a decimal place, okay? So whenever you see a decimal, then those zeros at the end, you're always going to count them in. Zeros in between are always significant. This comes into play when rounding. So if you multiply two numbers, your answer can't be more exact than the numbers used in the measurement. So if you have 67.893 times 2, that answer, 67.893, seems very, very exact. Like there's 5 significant figures in that. But then you multiply it times 2. Okay? So that is going to end up affecting the exactness of your number. So if you do the math, I have to do this math. 67.893 times 2. So I got 135.786. But I can't keep all of those significant figures. I have to round to the smallest number of significant figures in my problem. So that means I have to round this number 786. There's a 7. You didn't catch me on that. 786. I have to round that to just one significant figure. So what would I round this to? Okay, so not 1, 100. Okay, so what I do when I figure out how to round, I figure out how many significant figures I need. I start on the left and I just count how many significant figures I have to keep. In this case, I'm only going to keep 1. So that means the rest of them have to round, but I have to keep the size of the number. I can't go from 135.786 to 1 because that's like a whole lot smaller. Okay, I'm keeping the 1, but the rest of them are going to, since the next number is a 3, that's going to become zeros. So the answer would end up being 100. So my answer can't have any more significant figures than the significant figures in the problem. That's how multiplication and division work. Addition and subtraction don't follow this though. Addition and subtraction, you want to round to the similar number of decimal places. So if I have 12.68, 1.9032, and 0.865. You do the math, but I'm going to round to 2 decimal places because that's the number they all have in common. So you take 12.68 plus 1.9033, oh, sorry, 32, plus 0.865. So I got 15.4482. Okay, but according to this, and oftentimes I kind of look at it that way, like I forgot, I'm gonna like round all that stuff past there. I'm gonna keep 2 to 2 decimal places. So what do? If the next one is an 8, what will that do? You round up. Anything that's 5 or higher, you round up. So that means this 8 is gonna change this to a 5. So addition and subtraction, you round by the smallest decimal place they all have in common. But multiplication and division, you have to take it into account the number of significant figures in the problem.
You're counting the spaces after the decimal, right?
Mm-hmm. Yep, the ones they all have in common. Okay, so let's practice a couple of rounding. First, round to 4 significant figures for this one. So we said there's 6 significant figures, so I want you to round that to 4. So what I do, if I've got to round to 4, I start on the left. Remember, this 0 is not significant because it's a leading one. And I just like underline the number of significant figures I need to keep. So I know I need to keep 1, 2, 3, 4. So that means that the rest of that's going to have to go away. So the next number is a 6. So that's going to change the 5 to a 6. It's going to round it up. So if I rounded this to 4 significant figures, it'd be 1.206. What if I rounded the next one to just 2 significant figures? Not 1,300. 13 watts. So I can't go from $12,500 to $13. Like, that's not an okay round. Okay? You got to make sure that you're keeping the size of the number. So remember, those lagging zeros are not significant, but you still have to keep them when you indicate the size of the number. And I always think about it in terms of money. Like, I'm not going to take $12,500 and round it to $13. I'll keep my $12,500 if that's the case. So I have to keep those zeros to show the size. So in this, if I want 2 significant figures, I know I keep the 1 and the 2. And that means the next ones have to round. Well, the next one's a 5. We round up. 5 goes up, so that would be 13. But I keep those 3 zeros to indicate the size. Now on the one above, I already had a decimal place, so that's why I just dropped those ones off. But if you don't have a decimal place, you may have to place those zeros in there to keep the size. So for this one, what if you rounded to 2?
460.
So 2 means I start from the left. That means I'm keeping the 4 and the 5. That means that everything else is going to have to change. But the next number is a 6. So that'll cause me to round
But you have to put a decimal.
up. So it'd be 4, 6,
0 decimal.
and 0. And I wouldn't put a decimal,
Oh, 'cause it's
okay?
two.
Because I want 2 significant figures. Okay, so it's just 2 significant figures, it would round to 460. So it was 456, rounds up to 460. What about this one? If you round this to 2 significant figures, you start from the left. Remember, leading zeros are never significant, the ones out front. So you skip those. The first 2 significant figures you get to are the 2 and the 5. So that means that now 896 is going to change. That's going to cause the 5 to go up to 6. And you've got to keep the decimals. When you have a decimal place or the size of a number, you have to keep the decimal or those sizes. So if it's a number smaller than 1, you have to keep that decimal place. What would be 3 significant figures? 3. I don't count those zeros, right? Those aren't significant. So that means that I need the 4, the 5, and the 1. So the next 2 are just zeros. So what would I do? Just drop them off. But since it's a number smaller than 1, I got to keep that decimal size. So it'd be 0.00451. Oh, sorry. Sure. Oh, did I write 5? It should be 6. That should be 6. Sorry. I meant to. I just wrote it wrong. Okay, so let's look at some that come in with the calculation. So when you're looking at multiplication and division, you need to know the number of significant figures. Your answer should have the fewest number of significant figures is in the problem. So 0.120 times 2.782. How many significant figures in the first number? 3. The 120, okay? Because it's after a decimal, so that last 0 is significant. So there's 3 significant figures here. 2.782. 4 significant figures because they're all non-zero numbers. They're all measured values. So when you do the math, you're going to round to what? Round to 3. So when you get the whole number, it is 0.33384. And that oftentimes happens, like when you're doing math problems, you get these really big numbers. But this tells you how big the number should be. So I want to round it to 3. So remember, the leading 0 is not significant, so you don't count that 0 out front. So you count the 333. The rest of it I'm going to have to round. So what will it do? It'll round up. So 0.334. So since the number after is an 8, it's going to round that last 3 up to a 4. $12,500 divided by 3.7. 12,500 has how many significant figures? 3. No decimal place. The zeros at the end don't count. So there's 3 significant figures. 3.7 has 2. So that means that I want to round to 2 significant figures. 12,500, do the math, divided by 3.7. I know I want to round to 2. And I got 378.378. It's a really big number. So you start at the left. I underline the first 2 significant figures I come to, and that means the rest of them are going to have to change. So this is 3,378.378. So that will round. That 3 will become a 4. But you keep the zeros because you see that it keeps the size. I drop all the decimal place values off after that decimal place, but I want to keep those 2 zeros to indicate size. So we'll do one more. I'll let you do the rest of them, and we'll actually come back and look at these 2 at the very beginning of the next class. So 456.025, 2.30, 19.2544. Add them all together. How do I know how to round?
3 decimal.
3? 2 to what? 2 decimal places. Remember, addition and subtraction, you round to the decimal place they all have in common. Okay, so the middle one is 2.30. This one has 3 decimal places. This one's at 2. This one's at 4. So I'm going to round to 2 decimal places because it's addition and subtraction. So it doesn't matter about significant figures. Okay, it's the number of decimal places. So here, round to 2 decimals. And we get that 456.025, 2.30, and 19.2544. Oh, put that last number in wrong. So I got 477.869. No? No. No.
I got 477.5794. That's what I got.
477.5794?
Yes.
Okay, good. 477.5794. Okay, so you see how that goes out 4 decimal places, but you need to round to 2. So that means you're going to keep all of these, and then past that is where we're going to round. So the next number that you're going to round to 9, so that's going to change the 7 to a 8. So 477.58. So work on those ones. Also go back over those unit conversions and practicing them. So Monday, we'll go finish these, and then we're going to move forward looking at scientific notation, which is really pretty straightforward, back and forth from one to the other, percents, and then we'll talk about temperature, and that leads us right into balancing equations. We'll be finished with this chapter.